Good day. Our topic for today is matter and energy. I am Dr. Erwin R. Avrencil. So for our learning outcomes, first, explain the principles about matter and energy. Second, classify matter according to their structures and properties. Third, differentiate physical and chemical changes. Fourth, solve problems involving energy, temperature, and heat capacity. So the following is our learning outline. First is the introduction, classification of matter, changes in matter, conservation of matter, energy, temperature, and heat capacity. So our learning outline will serve as our guide or your guide during the discussion using this video lesson. So remember that there are also exercises that can serve as your practice exercises to check whether you have learned something from this lesson. So let us begin with the definition of matter. So since elementary, matter is already a topic in science. So by definition, we say that it is anything that occupies space and has mass. So basically, everything around us is composed of matter. So I am matter, you are also matter, and the distance between us or between the persons inside your house are also considered to be as matter. The air between you are also matter. So some matter is easy to see, like water, like wood, the laptop that you are using, the cell phone that you are using, your house. But other matter are quite difficult for us to see. For example, the air between you and the person beside you, the air inside your house, the air inside the balloon or the tire, and also the dust. The dust particles that are embedded in the air. So these are quite difficult for us to see. But still, even though we cannot be able to see them, they are also considered as matter. And the most basic building block of matter is the atom. So as we all know that atom is stated by Democritus a long time ago. By definition, from the word atomos, it is indivisible, it is uncuttable, it is the basic building block of matter. So that means that all matter are composed of atom. It could be a single atom, or it could be composed of different kinds of atom. And we are going to discuss that later on. So let us now proceed to the classification of matter. So matter are classified as to be pure substance, which are composed of element or compound, and mixture, which are considered or classified as a homogeneous mixture or a heterogeneous mixture. Okay, so we are going to discuss that one at a time. So for example, when we speak of pure substance, we're talking about it is a form of matter that has constant chemical composition and characteristic properties. So when we speak of constant chemical composition, the chemical composition of this particular substance is the same all throughout that particular substance. So that's why the examples given a while ago are elements and compounds, because when it comes with the elements, it is constant all throughout, and same as with the compounds. So it cannot be separated into components without breaking chemical bonds. So as we all know that specifically for compounds, they are connected by chemical bonds. And for us to be able to break compounds, we have to break the chemical bonds. So if we cannot break the chemical bonds composing the compounds, then therefore we are not breaking the compounds. So that's how complicated pure substances are. So for example, later on, we are going to discuss that further. So it can be solid, liquid, gas, or plasma. And of course, there are 5 states of matter, right? So solid, liquid, gas, plasma. and Bose-Einstein condensate. Of course, we are not going to discuss them further since these are all basic knowledge for you. So changes in temperature or pressure can cause substances to shift between the different pieces of matter. For example, solid can become liquid and liquid can become gas. Depending on the temperature. Let's say, for example, when you put liquid water inside the fridge, in the freezer, it will become solid. It will solidify. So therefore, there is a decrease in temperature. But when you put a certain amount of water in the let's say in your inside the, let's say, when you put the ice outside your freezer, it will melt simply because there is an increase in temperature from, let's say, from a 0 degrees Celsius to going to, let's say, 26 degrees Celsius, which is the usual room temperature. So it will melt. So there's a change in temperature, there's a change in pressure, there will be a cause, it will become a cause of a shift between different pieces of matter. Okay, so let us talk about mixtures. So material system made up of two or more different substances which are mixed but not combined. So you have to distinguish here the differences or the difference between mixed and combined. So when we speak of mixed, they are just physically combined. So by definition, it refers to the physical combination of two or more substances in which the identities of the individual substances are retained. So that means when we speak of mixture, it is quite different from that of the pure substance. Simply because in pure substance, let's say for compounds to be formed, there is a combination or chemical combination between elements in a certain proportion. So when we speak of mixtures, you are just combining them physically. So for example, you just mix sand and water. So the identity of water is there and the identity of sand is still there. Or when you mix, let's say, cabbage, carrots, kangkong, pechay, and different vegetables. So they are still vegetables. They retain their properties. Thus, you are just mixing them. So that is still considered as mixture. But when you create a certain chemical reactions in order for it to combine or chemically combine two different elements or a compound with another compound or element with a compound, then you are not creating mixture but you are creating another compound. So it is easier for you to see it as long as the identities are still there, so they are considered to be as mixture. But if the identities are different from the original after mixing it or after combining them, then therefore that is no longer just a mixture, but it might be already a compound. Okay? So take the form of solutions, suspensions, and colloids. So these solutions, suspensions, and colloids are actually types of mixtures. So let us discuss further what elements are, what compounds are. So this time, specifically, we're going to discuss pure substances. So what are elements? So of course, you have encountered this a lot during elementary or even during high school. You have encountered this one. So this is, they are the simplest complete chemical substances. Simplest because you can no longer break, unless you would like to go into the atomic level, but when it comes to the pure substance, that's the simplest chemical substance. Each element corresponds to a single entry on the periodic table. So one element is one entry in the periodic table. Let's say silicon or lithium or hydrogen. Or they are also considered to be as material that consist of a single type of atom. So when we speak of element, let's say oxygen element. So all oxygen element is composed of a single type of atom, which is an oxygen atom that has a certain unique characteristic that is only found in that particular oxygen atom. So it is a different story if you are going to analyze, let's say, lithium. So lithium atom is different from that of an oxygen atom. And oxygen atom is different from that of, let's say, magnesium atom. So the point is that type of element is consists of only one type of atom. So elements cannot be divided into smaller units without large amounts of energy. So back in the days, Democritus has stated that there will come a time that when you found a certain rock, there will come a time that you can no longer break it. So that is the indivisible or uncuttable part of a matter, and he called that as atomos. From the word atomos, we get the term atom. Now, elements are composed of atom, and elements cannot just be broken down into atoms without, or from atom to protons or to electrons without large amount of energy. Okay, so that's it, and we call it now as nuclear energy. So it is a different story, but elements cannot be divided, period, okay, without large amount of energy. So each atom type contains the same number of protons. So for example, hydrogen has only one proton. So when you increase that into two, it is no longer be called as hydrogen. It is now called as helium, because helium has two protons. So same thing as with lithium, with beryllium, with oxygen, and all other elements in the periodic table. So they follow the same rules. So the periodic table of elements is ordered by ascending atomic number. So hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, and so on and so forth. So elements are further divided into metals, metalloids, and nonmetals. And one good thing about periodic table, they are arranged accordingly. No? So they are arranged not only according to the atomic number. By the way, atomic number is the number of protons. So therefore, if helium has two atomic number, then therefore it has 2 protons. If carbon has 6 protons, then it has 6 atomic number. So in short, the periodic table tells us a lot about the atoms, or about the elements. So that's why it is called as periodic table of elements. So you will not just call it as periodic table or table or periodic. So you have to call it as periodic table of elements. Now, in this particular example, as you can see, they are classified according to metals, nonmetals, and metalloids. Of course, there are characteristics that are only observable to metals, observable to nonmetals, and there are combination of metals and nonmetals, and these are known to be as metalloids. Now, to give you some information when it comes with the characteristics of metals, some of them are they are good conductors of electricity, they are good conductors of heat, they are mostly lustrous or shiny, and so on and so forth. They are positively charged. No, like for example, lithium is +1, sodium is +1. Let's say iron is also positive, and so on and so forth. Now, on the other hand, nonmetals are they possess characteristics that are opposite of that of the metals. No, if metals are good conductor of electricity, the nonmetals are poor conductors of electricity. So that's why they are known to be as they are used as to protect a certain let's say a certain metal to electricity. Okay, insulators of electricity, insulator of heat, because they are poor conductor of heat, poor conductor of electricity, and they are not shiny unlike metals. And of course, when it comes with the charge, they are negatively charged. Let's say, for example, chlorine is -1, fluorine is -1, bromine is also -1, oxygen is -2, and so on and so forth. Now, there are cases when elements possess certain characteristics of a metal and a non-metal, and we call them as metalloids. So, in this periodic table that we are looking right now, the pink ones are metals, the blue ones are non-metals, and the green one at the middle are considered to be as metalloids. So they possess a certain characteristics of a metal and a characteristic of some characteristics of a non-metal. So you cannot classify them as metal, you cannot classify them as non-metal. So another classification was made solely for this kinds of elements. So these are boron, silicon, germanium, arsenic, antimony, and tellurium. Okay? So let us now continue. So these are compounds. So chemical bonds link elements together to form more complex molecules called compounds. So basically, compounds are composed of different elements combined together, chemically combined together in a certain proportion. I'm saying it is in a certain proportion because compounds are made in a certain number of atoms. So you cannot just put together different elements and expect that there will be compounds at the end. So there should be certain proportion, number of atoms bonding together, and they should be chemically reactive. Now, but basically, when we speak of compounds, they are composed of elements bonded together. So these bonds are known to be as chemical bonds. Now, compound consists of two or more types of element held together by covalent or ionic bonds. So covalent and ionic bonds are basically the types of bond, and we are going to discuss that later on a separate discussion. Okay? So, but for the meantime, when we speak of compound, it could be covalent compound or ionic compound, because covalent compounds are made by covalent bonds. So elements are bonded together with a covalent bond, and ionic compounds are bonded together with ionic bonds. Okay? So, most elements on Earth bond with other elements to form chemical compounds. Well, it's a blessing, because if we are going to follow the Big Bang, from the Big Bang, atoms were created, elements were created, and if elements were not that reactive, then therefore wala tayong lahat ngayon, because we're composed of compounds. Okay? So, for example, sodium is attracted to chlorine. So sodium has +1 charge, chlorine has -1 charge. Then they form a very stable compounds known as sodium chloride, or simply known as table salt. So yung asin na ginagamit natin sa mga bahay-bahay natin, sila ang tawag natin doon ng table salt or sodium chloride. And of course, another example is water. So 2 atoms of hydrogen and 1 atom of oxygen form H2O, or known as water. So this is what I'm saying a while ago, that these compounds are formed in a certain proportion of atoms. You cannot just combine 3 atoms of hydrogen with 2 atoms of oxygen. So basically, nothing will happen. So there is what we call a certain proportion, so that a certain compound will be formed. So the 2 or more component elements of a compound can be separated through chemical reaction. So compounds are made via chemical reactions, and then therefore you can only separate them via chemical reactions also. So that's why it is known to be as pure substance. So by definition a while ago, it is difficult to separate them, and it can only be done through chemical means. So the picture on the right is the usual table salt. Okay, so yeah. So chemical compounds have a unique and defined structure which consists of a fixed range of atoms held together in a defined spatial arrangement by chemical bonds. So this is the one that I'm saying a while ago, that they are made by a certain proportion so that they can be able to form that particular compound. Okay, so that is fixed ratio of atoms. So let's say for water, which is made of 2 atoms of hydrogen and 1 atom of oxygen, so that is 2:1. So 2 atom of hydrogen to 1 atom of oxygen. So that is a fixed ratio for water, and all compounds are doing that. So chemical compounds can be molecular compounds held together by covalent bonds. So there are a lot of covalent bonds, and there are a lot of molecular compounds that are held together by covalent bonds. And of course, we're going to discuss that in a separate discussion. So salt are held together by ionic bonds. So there are also what we call as metallic bonds. So intermetallic compounds are held together by metallic bonds, and complexes held together by coordinate covalent bonds. So basically, compounds are arranged, or they are connected to each other by chemical bonds. All right, so let us now proceed to mixture. So we are done with the pure substances. What are they again? They are elements and compounds. So let us now proceed to mixture. Okay, so a while ago we said that mixtures are classified as either a homogeneous mixture or a heterogeneous mixture. So this time let us discuss them. So a homogeneous mixture is a mixture of 2 or more chemical substances. It could be an element or a compound where the different components cannot be visually distinguished. Okay? So when we speak of cannot be visually distinguished, meaning to say that when you mix them, you are not chemically combining them, you're just mixing them. You cannot see visibly the component. So meaning to say, when you mix them together, you cannot see the components. You know that they are there, but you cannot distinguish them. So a very good example actually of mixture is a solution. Let's say when you add salt in the water and you mix them thoroughly, and you cannot be able to see the salt, but when you taste the water, it is salty. So that is a homogeneous mixture. They are evenly scattered in the mixture, and you cannot be able to distinguish. Of course, you can see the water, no? Baka kasi isipin mo na, teka, kita naman yung water. It is not, no? That is not the logic there. What I'm saying is that you cannot see the one that you mixed with water. Okay? So often separating the components of a homogeneous mixture is more challenging than separating the components of heterogeneous mixture. Since it is homogeneous, meaning to say it is one phase system, you cannot just separate them. No? Were you able to separate easily salt solution? So for example, when you mix salt with water, can you easily remove the salt from the water or the water from the salt? So it is difficult, but it can be done, no? But the point of the argument is that heterogeneous mixture, and you will find out later on, it is easier for them to be separated, no? Unlike in a one-phase system or a homogeneous mixture. All right. So a mixture, yeah, this is the homogeneous mixture solution. So of course you have to remember, no, that in a mixture, particularly in a solution, there's what we call a solute and a solvent. So basically in a solution, the substance that has more amount is considered to be as the solvent, and the one with a lesser amount is known as the solute. Now in this example, water is the solvent and sugar is the solute. So you have to, when you combine them, you call it now as sugar solution. So completely dissolved to the atomic level. So you cannot be able to see them. Even though, of course, when you use the electron microscope, for sure you can be able to see them. And particles cannot be seen by the naked eye. It cannot be filtered. No, when you filter a sugar solution or even a salt solution, do you think you can be able to collect the salt or the sugar in the filter paper? Of course not. No, the taste of the water are the same. If it is salty, then it is salty. If it is sweet, then it is sweet. So, of course, examples of this sugar and water. So when you mix them, they are thoroughly mixed, and then the taste from top to bottom are the same. Okay, so let us now proceed to heterogeneous mixture. So why is it hetero? So in a homogeneous mixture, we say that it is one-phase system. Now, yes, in a heterogeneous mixture, it is a two or more phase system. So depending on the kind of material that are mixed together. So one good example of here is suspension. So doesn't mix at all, no? So the form layer, they can be separated by filtering mixture. Example of this is sand and water. So when you mix the sand and water, if you are going to shake them well, at first they will mix as if they are mixing, but later on, after some time, the solid substances will be collected at the bottom of the container, and the water will become clear, and you can be able to see that they did not mix at all. So since it is they don't mix at all, it is easier for us to separate them. All you have to do is to get a piece of let's say a piece of cloth that will serve as your filtering device or filtering filter paper, and then you can transfer the water, and then you can be able to collect the sand in the cloth or in the filter paper, and that's it. You can be able to separate them. Unlike in solution, it is difficult for you to do it, right? Okay, so let us now proceed. So another one is a colloid. So colloids are considered also a heterogeneous mixture. So the characteristics are mostly dissolved, mostly but not all. So meaning to say they are mostly dissolved, but there are parts which are not dissolved. So some pieces of solutes still clump together. So that's why they are not dissolved by the solvent, because they keep on clumping together. So usually opaque or cloudy, light spread out when shown through mixture. So meaning to say, if you are going to get a flashlight, and you will allow the light of the flashlight to pass through the colloid. So light, instead of passing through or not passing through, it will spread out. Okay, so examples of these are milk and water. Okay, so in milk, if you are going to look at in a certain example of milk, they are mostly dissolved, but if you will look closer, there are parts which are not dissolved properly. They are still clumping together. Okay. And of course, fog is also a good example of a colloid. All right. So, distinguishing between homogeneous and heterogeneous mixtures is a matter of the scale of sampling, which is good because for you to be able to distinguish, you have to look into the samples. So, on a small enough scale, any mixture can be said to be heterogeneous because a sample could be as small as a single molecule. And in practical terms, if the property of interest is the same regardless of how much of the mixture is taken, the mixture is homogeneous. So, in short, no, it is for you to be able to analyze a certain, you have to analyze the sample for you to be able to say whether it is a heterogeneous mixture or a homogeneous mixture, following all the characteristics that were given to you a while ago. So a mixture's physical properties, such as its melting point, may differ from those of its individual components. For example, when you mix water and alcohol, no, alcohol has lower boiling point, has a lower boiling point than water. So meaning to say that as if even though the mixture is not yet boiling, let's say there are more water than alcohol, it doesn't mean that the alcohol is not evaporating. So because in a certain substance, when it is hot already, especially if it is boiling, it will continuously evaporate, no? Because the molecules will become active. Now, in boiling alcohol solution, so you might think na it is not yet, that the alcohol is not yet evaporating. Or in fact, if you reach the boiling point of the alcohol, it will not boil because there are more water than alcohol, but it will evaporate. The alcohol will eventually evaporate ahead of water. Okay? So, some mixtures can be separated into their components by physical or mechanical or thermal means. Let's say when you mix iron filings with that of sand, or when you mix iron filings with that of salt. So all you have to do is to use magnet. So that is utilization of magnet to separate the components. No? So when you magnetize the mixture, only the one with a metallic property will be able to stick to the magnet, and you can be able to separate them. So that ends the classification of matter. So let us now proceed to states of matter. Now, we will only be focusing on the three states of matter: solid, liquid, and gas. So these are basic, no? Because these were topics even in the elementary, no? Solid, liquid, and gas. So by definition, solid closely packed particles with fixed location. Closely packed meaning molecule of a solid cannot move from one place to another. Liquid closely packed particles but free to move around. They're closely packed particles but they are moving, but they are flowing. And gas, great distances between particles with free movement. Now, you can be able to see that in this particular example. No? So solid, liquid, and gas, and the one at the bottom are the illustration of the molecules in that particular example. So in this one, they are solid metal. So the particles are compact, and each particle cannot move from one place to another. So meaning to say na one molecule will just vibrate on its own, on its position, but it will not move into the another position, unlike in liquid and gas. And one thing about gas and liquid is that since they are flowing, no, they can conform the shape of the container. No? Well, back in the days, you will just be asked, liquid can uh, can conform with the shape of the container as well as the gas. But how is it possible? No, simply because of the molecular structure. No, so there are spaces between them, so they are flowing. So whatever the shape of the container is, they will take that shape. Okay, so that's why also when it comes to gas, no, why are gas molecules compressible? Simply because of the distances between them, no. So we can say that air is light. You cannot just get air and then you throw it to somebody, because the molecules of air will just scatter. But what if you put the air inside a container? Let's say you get the interior of a tire, no, or timbulan or salbabida, lagyan mo ng hangin, siksikin mo doon, no, and then it will solidify, almost solid, and then when you hit somebody, no, it's like the person will receive solid object, because gas molecules can be compressed. And of course, please do not do that, because you are hurting somebody, right? So the tire of the vehicle, when you compress the gas inside, there's a certain pressure in the air of a certain tire vehicle, and then that's why it looks like solid. That's why it can run. That's why you can use it as your tire, because of the air inside. Same as with balloon, same as with airbed, same as with other things that utilizes air inside. So they are compressible, highly compressible. So let us now proceed to the properties of the states of matter. So these are solid, liquid, and gas. So these are actually the things that I explained a while ago. No, so solid can only oscillate, meaning they can vibrate about fixed point. So they cannot move from one place to another. So they are very close together. The shapes of solid are definite. Volume is also definite, and they are incompressible. If solid can be compressed, then that is not entirely solid. Okay. Liquid, so free to move relative to one another. That's why they are flowing. They are still close together. The shape is indefinite, because that depends on the shape of the container, and the volume is definite, because you cannot change the volume of a liquid. No, if let's say you took 250 ml, no matter what you do, you put it in a different container, they are the same. So that's why they have an exact volume, but still they are incompressible. So you cannot compress 10 gallons of water in just one glass, in one cup container. So you cannot do that. Now, when it comes to gas, they are free to move relative to one another. They are far apart. They are indefinite when it comes with the shape, because they conform the container. The volume is also indefinite, because the volume of gas is dependent on two factors. One is pressure, and another one is temperature. So the more the hotter the place is, there will be constant volume. There will be constant movement of the air molecule, thus increasing the volume of air. Okay, so same thing as with pressure. Now, a good example of that is the hot air balloon. So at the beginning, the hot air balloon has no air inside. Then there will be a source of flame, and then you'll be able to see that slowly the hot air balloon will rise, and then it will float in the air, and then that's it, because of the volume of air inside, because of the increase in temperature. So how can you lessen the amount of air inside the hot air balloon? So simply you have to lower the temperature. Let's say you have to lower the flame. So will slowly go down. Now, in this time, so you are to answer exercise number 1. Number 1A. So this will serve as your practice exercise. And the directions, classifying the following examples of matter as pure substances or mixture. So first classification, you have to classify it first as pure substance or mixture. And if it is pure substance, you have to classify it further into elements or compounds. And if it is mixture, you have to classify them as homogeneous or heterogeneous. And if it is homogeneous, classify it further as solutions. And if it is heterogeneous, classify them further as suspension or colloids. So you are only given 2 minutes, but you can pause this video so that you can be able to answer this. Okay, so let us now move on. So congratulations for finishing the first part of this video lesson. I hope that you were able to get a perfect score in the exercise number 1A. So let us now proceed to changes in matter. So a while ago we say that matter change. So some of them changes from one phase into another. Let's say from solid to liquid, liquid into gas, gas into liquid, and gas into solid, and so on and so forth. But there are specifically explanation about changes in matter. So physical chemical changes are closely related to definitions of physical and chemical properties. So meaning that physical changes are connected to physical properties, and chemical properties are connected to chemical changes. Now, when we speak of physical change, matter changes its appearance but not its composition. So meaning to say, when you cut the paper, you cut it thoroughly, you cut it into tiny pieces, but still it is still paper. When you cut a certain metal, when you cut your hair, as long as you just cut it, and you did not change its composition, it is still paper, it is still hair, it is still metal, then these are just examples of physical changes. Now, a good example also is water. So water is in liquid. The usual state is liquid, and then when you put it inside the freezer, it will turn into solid, but still it is water. When you put it outside the freezer, it will go back to being a liquid water, which is still water. And when you boil them and it starts evaporating, it will become water vapor, and that is in a form of a gas. And gas, water vapor, that is gas, ice, which is solid, and water as liquid, they're all water. So those changes in matter when it comes to water is considered as physical change. Now, chemical change is a different story, because those matter undergoing chemical change also changes its composition. So meaning to say, after the change in matter, if it is chemical change, the original characteristics is no longer observable. So it's gone already. It is there's a change in composition. It is a new product already. Now, chemical changes occur through chemical reactions. So chemical reactions are done. Chemical changes can be expressed by a chemical reaction. So as long as there are chemical reactions, there are chemical changes. And when there are chemical reactions, there will be reactants. And reactants will be converted into products. And these products are different from reactants. Thus, chemical changes occur because there is a change in composition. As simple as when you burn the paper, it's no longer paper. You cannot even see any mark that it is paper because it turned into ash. When you burn certain leaves, you can no longer identify that these are leaves because they are all converted into into ash. When you see that your roof become rusty, so inalawang yung bubong nyo, you can no longer see the presence of the roof, but they are, or the metals, but it is composed of rust particles which are different in composition. So all these examples are known to this chemical change. Alright. So a good example here is this lighter, physical change and chemical change. So physical change, liquid butane, when liquid butane escaped from this lighter, so from being a liquid butane, it became liquid or gaseous butane, but still butane. So there's no there's no change in composition, it's still butane, therefore it is considered to be as a physical change. Same thing as with water, right? So when you boil water, it evaporates, then it becomes water vapor, and then still water. Now, on the other hand, the one on the right, it is a chemical change. So liquid butane, because of the spark, in the lighter, it created flame. So liquid butane is no longer butane, but the products include carbon dioxide and water molecules, and that's considered to be as chemical change. So let us now look into the conservation of matter. So since there is a change in matter, in physical change, we can easily see the conservation of mass. When you cut 1 kilogram of paper, at the end of it, still a paper, 1 kilogram paper. But conservation of mass can also be seen in chemical changes or in chemical reactions. So according to this law, during any physical or chemical change, the total mass of the products remain equal to the total mass of the reactant. So it is easier for us to tell when you cut 1 kilogram of paper, at the end of the process, still it is 1 kilogram, though there are a lot of pieces. Now, in the chemical reactions, that's why we balance chemical reactions. It is because of the conservation of mass. So that means when a certain mercuric oxide, which is 100 grams, was decomposed into atoms of hydrogen and atoms of oxygen, atoms of mercury, and atoms of oxygen. So 92.6, which is the mass of mercury, plus 7.4, which is the mass of oxygen. So it will still 100 grams. Okay, so conservation of mass. Though the reaction here is not yet balanced, the point of the argument is that the mass of the reactants should be equal to the mass of the product. Okay, so another way of stating that is, in a chemical reaction, matter is neither created nor destroyed. The law of conservation of mass is also known as the law of indestructibility of matter. So they are indestructible. So that's why mass is always conserved. Okay, in this example, when you burn the wood, tap into the wood, it turns into ash. But let's say, for example, the wood is 5 kilogram. Is the ash also 5 kilogram? No, it is lighter because the product of the flame or the product of burning wood is not only the wood, it's not only the ash. There are also other products, and when you add all these products, the mass will be the same as that of the reactants. So that's why it is there is conservation of matter. Alright, so let us now move on. So let us move on to energy. Okay, so one thing that is also concerned about matter is the energy. Okay, so by definition, we say that Physical and chemical changes are accompanied by energy changes. Well, of course, no. Energy is by definition, the capacity to do work, and work results from a force acting on a distance. So, for example, when you push the cart, when the person push the cart going to the box going to the right, there's a force acted on it, and there's a certain distance, so there's a work, and the man utilizes energy, which is the capacity to do work. So these are the types of energy. First, we have the potential energy, or the PE, energy due to the position or composition of the object. Of course, I'm sure that you are familiar with this. And then kinetic energy, or KE, energy due to the motion of the object. So simply, potential energies, energy at rest; kinetic energies, energy in motion. When you are walking, there is kinetic energy. When you stop, so there is potential energy. A potential energy is a possible energy in motion. Possible, but not yet in motion. An object's total energy is the sum of its potential energy and kinetic energy. So, the law of conservation of energy states that energy is neither created nor destroyed, just like in the conservation of matter. So, a while ago, we said that matter is indestructible because we can conserve the mass. So same thing as with energy. So energy can change from one form to another, or transferred from one object to another, but you cannot create nor destroy energy. Okay? So the picture on the right is an illustration of a potential kinetic energy. So the 10 kilogram iron on top of the building, due to its position, has high potential energy, which is unstable. Now, once it fell, the potential energy is converted into kinetic energy, and then once it hit the ground, so it is now stable, so it has a low potential energy. So as long as if the object is that has potential energy is unstable, it will most likely be converted to kinetic energy. So usually these are objects that are found on top of a certain object, let's say on top of the cabinet, on top of the building, on top of the house, on top of the tree, and so on and so forth. Now, because of their instability, it will be converted to kinetic energy. And then, once it hits the ground and there is a stable position, so it is considered now as low potential energy. Okay, let us talk about specific types of energy. So first is electrical energy, is the energy associated with the flow of electrical charge. So the one that we utilize in charging our cell phone, in charging our laptop, the lights, the air condition, and everything that we use for our appliances at home are considered to be as electrical energy. And thermal energy is the energy associated with motions of particles of matter. And chemical energy is a form of potential energy associated with positions of particles in a chemical system. So food, the energy found in our food is considered as chemical energy. So let us now look into energy unit conversion. So of course, way back in high school, we were taught about conversion of units. So we will no longer discuss that here, but you will be asked to convert energy units. So these are the units for energy. So 1 calorie or 1 cal is equal to 4.184 joules. 1 calorie is also equivalent to 1,000 calorie. And 1 kilowatt hour or kWh is equal to 3.60 times 10 to the 6 joules. So these are conversion units, conversion table for energy that you need in order for you to convert problems from how many, let's say, when you look into the food labels, let's say in one bar of chocolate, there are around 250 calories, no? So how many joules, or how many joules are equivalent to that particular number of calories in, let's say, in a chocolate bar, and so on and so forth. So chemical reactions can either be exothermic or endothermic. Exothermic release energy to surrounding, let's say combustion. When you burn something, no, so it is an exothermic reactions, because there is a release of energy to the surrounding. So that's why we can be able to feel increase in temperature. And the other one is endothermic, absorb energy from the surroundings. A good example of that is photosynthesis process. So in photosynthesis process, they absorb sunlight energy, and with the use of carbon dioxide, they can be able to produce food. And that is a good example of energy absorption. So using the heat from the sunlight energy, first the light energy from the sun absorbed by the majority of the leaves of the plant. Now, the one on the right is a diagram of energy. So endothermic reaction and exothermic reaction. So the one on top is exothermic reaction. You have the reactants in the products. Reactants, energy release to the products, and in the endothermic reaction, reactants with a low energy is absorbed going to the product with a high amount of energy. Now, let us now proceed to this exercise 1B. So I provided you with food labels of certain products that you have to convert into calories, into energy. So using the following food labels, solve the number of joules for the given calories per serving. So, for example, in the first data, you have there 210 calories per serving. So you are only asked about per serving, which is around 1 cup or 240 ml. So 210 calories. So how many joules? In number 2, this I think is oatmeal, no? So nutrition facts. So serving size 1/2 cup dry, 40 grams. Calories is only 140. Okay, so convert that also into joules. Okay, so you are given a few minutes in order for you to solve this, and then you can pause this video so that you can be able to have plenty of time to answer this. So this is to check whether you have learned something in our previous discussion. And then if you think that you cannot be able to solve the problem, and then you can just go back to the discussion and then look for the conversion of units. All right, so let us now proceed to thermal energy. So atoms and molecules of matter are in constant random motion, which is the source of thermal energy. So the more motion there are, the more thermal energy. Okay, so temperature is the measure of the thermal energy of a substance, meaning the higher the temperature, the more vibration there will be in a certain matter, and there will be thermal energy in that particular substance. So the hotter an object is, the greater the motion of its particles, and the greater the thermal energy. So just like in when you boil water, no? So there will be greater motion in the particles. That's why it keeps on evaporating, and then we can be able to observe the higher thermal energy in that particular example. And heat is the transfer or exchange of thermal energy caused by temperature difference. Okay. So with that, here are the temperature scales. So we usually use Fahrenheit, Celsius, and Kelvin scale. Okay. So the term absolute zero is connected with that of Kelvin. And then in 0 degrees Celsius or 32 degrees Fahrenheit, water freezes. So in around 100 degrees Celsius or 212 degrees Fahrenheit, water boils. Okay? Usually for human temperature as well as in animals, even weather, no. Usually here in Asia, we use degrees Celsius, especially here in the Philippines. But in other countries or even in other parts of the world, like in the US or in the Europe, they use Fahrenheit. And then Kelvin are utilized in getting the temperature or expressing the temperature of stars and planets. Usually a huge amount of temperature. And these are the temperature conversion. So, or the formula in converting. No? So the first one is how to convert Fahrenheit to Celsius. Convert Celsius to Fahrenheit on the second formula. Convert Celsius to Kelvin. Convert Kelvin to Celsius. Okay? So, with that, we are now into the last, on the third exercise. So, you are being asked to convert the following temperature to the given units. In order for you to practice this, you have to show solutions. Okay? So not just click the Google and then convert this and that, or click your cell phone, convert this and that. So better if you will learn how to convert units or to solve problems using a longhand. Get a piece of paper and then solve it. So you're given a few minutes to do this. And again, if you think that you need more time, and then just pause this video and then proceed when you are done. Okay, so we are now down to the last topic for this video, which is the heat capacity. So when you heat a substance, its temperature changes. Basically, it will increase. No? The temperature of the substance increases, and the amount of change depends on the substance. And the heat capacity is the quantity of heat needed to raise the temperature of substance by 1 degree Celsius. So meaning to say that depending on the substance, no, let's say when you heat a metal, it will easily increase the temperature. But when you heat a non-metal, for example, let's say a rubber or let's say a wood, it will take a lot of time. So the heat capacity of a substance is the quantity of heat needed to raise the temperature of a substance by 1 degree Celsius. And the specific heat capacity is the quantity of heat needed to raise temperature of 1 gram of substance by 1 degree Celsius. So do not be confused with heat capacity and specific heat capacity. Usually, the specific heat capacity is standard, no, when it comes with the different objects, no, just like the following. For example, lead has a specific heat capacity of 0.128, gold is 0.128 joule per gram degree Celsius. Silver is 0.235 and so on and so forth. So these are standard. Now, energy and heat capacity. So heat absorbed and temperature change are directly related as shown in the equation below. So that's it. So heat is equal to mass of the sample times a specific heat capacity of the sample, and then temperature change. For you to be able to get the temperature change, usually you will encounter two sets of temperature in a problem. So the one from the base temperature going to another temperature usually increases. No, so that means for you to be able to get the change in temperature, final temperature minus initial temperature, and you can be able to get delta T. And then you will simply multiply the mass of an object and then the specific heat capacity of an object. So that's given depending on what is written on the table a while ago. And then follow the formula, and you can be able to get the answer. Okay, so that's why your last activity for today is about problem solving on the specific heat capacity or heat capacity of a substance. So number 1, a 250 gram cube of lead is heated from 25 degrees Celsius to 75 degrees Celsius. How much energy was required to heat the lead? Okay, so you can be able to see the change in temperature. And then number 2 is that a 45 gram metal is heated 300 degrees Celsius with 3,500 joules of energy. What is the specific heat of the metal? So all you have to do is to convert the formula given to you a while ago. Okay, so I hope that you have learned something on this discussion, and I hope to see you again in our next topic. Thank you so much, and keep safe.